in an atom, electrons in the innermost orbits, already I discussed in the last class, which are filled called valence electrons. On the other hand, electrons in the outermost orbits, they are called as the conduction electrons. Now, valence electrons and the conduction electrons. This is the difference between these two. Innermost orbit electrons are valence electrons. Outermost orbit electrons are your conduction electrons. Now, with a crystal, every electron has a unique position and they are having a different pattern of surrounding charges. That's why each electron has a different energy level. Now, these energy levels, with a continuous variation of energy, they form the energy bands. Now, this energy bands, this is important for us. Now, what is energy band? The energy band, which includes energy levels of the valence electrons, is called valency band. If the energy band, which contains the energy levels of the conduction electrons, that you are calling as a conduction band. Now, always electrons, they move from the valency band to conduction band. Our semiconductor physics related to valency band and conduction band. Now, that's why I'm introducing what is a valency band, what is a conduction band. Now, what is a valency band? Valency band is a band which contains energy of valence electrons. What is a valence electron? The innermost orbit, what the electrons we are having in the innermost orbit, those are valence electrons. Those electrons are having energies. Those energies, they are forming as a band, that is a valency band. Now, what is a conduction band? Now, it is an energy band. These two bands are energy bands, which is above the valency band. Conduction band is above the valency band. When the electron move to conduction band, if you supply any external energy, then the electron move from the valency band to the conduction band. Now, this is, I will show you the simple slide here. Now, this is a valency band and this is your conduction band. The difference, the gap between these two, you're calling as the energy gap. This is a forbidden gap you're calling. Okay. Now, the last completely filled at the 0 Kelvin is called the valency band. That means in the valency band, it is a completely filled one. Okay. The next band with higher energy is nothing but conduction band. Now, the conduction band can be empty or partially filled. Generally, at the 0 degrees Kelvin, at the 0 degree, it is not at the room temperature. At the 0 degrees Kelvin, the band is, the valence band is completely filled. The conduction band is, it is not completely filled, it is partially filled. Is it clear? Can anyone text me? Are you able to follow my class? Okay, okay. Okay. Now, valence at 0 degrees Kelvin, the valence band is completely filled one. At the 0 degrees Kelvin, the conduction band, it is empty or it may be partially filled. Now, at the room temperature, that is at the 300 degrees Kelvin, now some of the electrons, they will get, that means the small energy or something, that means temperature is increased. Now, some of the electrons from the valence band, they may move to the conduction band. Okay, that we'll see in the next slide. Now, the energy difference between the bottom of the conduction band, this is the bottom of the conduction band, to the top of the valency band, this you are calling as a band gap. Just I'm introducing the terminology. What is valency band? What is conduction band? What is a band gap? And what is a Fermi level? Now, this terminology is important if you want to move the further. Now, what is a band gap? It is the energy difference between the bottom of the conduction band to the top of the valency band, that we are calling as the band gap. Okay, we'll see for the solids now how the band gap will be. In case of insulators, the band gap is very, very high. Now, that's why larger amount of supply is required to move an electron from valency to conduction band. Take an example of a wood. Even though you are supplying the larger amount of electricity energy also, it is very difficult to move from valency to conduction band. Now, in case of your semiconductors, the band gap is very, very, it is not very close. It is not very high compared to the insulators. Now, depending upon the crystal, if we take a silicon lattice or if you take the germanium material, they are having their own band potentials, built-in potential. If you apply that potential, now we can easily move electron from valency band to conduction band. And now see, this is for the conductors. For the conductors, almost the conduction band, valency band, these two will be there. Almost they are merging. Now, even though you are not supplying any external supply, all the electrons from valency band, they can move to the conduction band. Okay. Now, this dotted line, this we are calling as a Fermi level. What is the Fermi level? The top of the available electron energy level at low temperature. The position of Fermi level with the relation to the conduction band is a crucial factor. Now, next slides, when you go for the PN junction, now where is this Fermi level? Whether it is near to conduction band, near to valency band, that will define the motion, the movement of your electrons. Now, that we are going to see in the next slides. Okay, just now I discussed. Once again, I'm putting as a text format. In case of metallic conductors, conduction band overlaps on the electrons in the valency band. In insulators, there is a large gap between both these bands. Hence, the electrons in the valency band remain bound and no free electrons are available in the conduction band. Semiconductors have a small gap between both these bands. Some valence electrons gain energy from external sources and cross the gap between the valence and conduction bands. Now, by this movement, they create a free electrons in the conduction band and a vacant energy level in the valency band for other valence electrons. This creates the possibility of your conduction. Just read this text. Now, what I explained just now, the same thing I kept as a text fashion here. Okay, now we are moving on to our actual thing, that is a semiconductor. Now, what is a semiconductor? A semiconductor material is one whose electrical properties lie in between those of insulators and the conductors. Okay, in terms of energy bands, the semiconductor can be defined as those materials which have almost an empty conduction band and almost filled valency band. This just now I discussed in the previous slide. And the energy gap, the band gap is in the order of your 1 electron volt, which is separating the conduction band and your valency band. Semiconductors are two types. Okay, this already last class you listened all these slides. Now I am not going to discuss in detail. Just I will flash these slides very quickly. There are two types of semiconductors are there: intrinsic semiconductor, extrinsic semiconductor. Other name of intrinsic semiconductor is pure semiconductor. In my lectures, I may use some cases I may call as a pure semiconductor, or I may use the intrinsic. Both words will be the same. Or extrinsic I may use, or the impure semiconductor also I may use. Okay, the extrinsic semiconductors are two types. That is the N-type semiconductor and that is your P-type semiconductor. Now, what is an intrinsic material? Intrinsic material is nothing but your purest form of your material, now which contains equal number of electrons and holes. Now, semiconducting material which has not any impurities is called the intrinsic. That's why it is called as a pure semiconductor. In intrinsic material, the number of electrons and holes must be equal because they are generated in pairs. Electron hole pairs will be generated. For example, if you are taking 50 electrons are there, the same amount of holes will be present in the intrinsic material. Now the density of your intrinsic material 1.45 into 10 power 10 per centimeter cube. Just remember the intrinsic carrier concentration, because when we are solving the problems, if you have not mentioned any intrinsic carrier concentration, this is a fixed values at room temperature. This is now therefore for intrinsic material, now see, this is an intrinsic material. This is the valency band and the conduction band. Valency band is having maximum amount of its electrons are there, holes are there. Here also some electrons are there, holes are there. Okay, if equal number of electrons are there, holes are there, this is the Ni. Np is equal to Ni square. This you are calling as a mass action law. Just remember this this one formula. This is the mass action law. In the intrinsic material, equal number of electrons and holes are there. That's why Np is equal to Ni square. And this relationship you are calling as a mass action law. Just remember this equation. It will be useful for us when we are solving the some problems. Now, what are extrinsic semiconductors? These are the doped semiconductors or the impure semiconductors. Already I discussed in the last class. Now, why we are going for the extrinsic semiconductor? All the physical, whatever the nowadays the devices we are having, all the devices are extrinsic semiconductors only. Now, you cannot design anything with the intrinsic semiconductor. Now, already I discussed in the last class. Why? Because in the intrinsic semiconductor, the carrier, for example, if I want to consider the electron charge, 50% only it is going to constitute. For example, movement of electrons is the charge of electron. If you take the motion of electron is very high compared to the hole. Now, for example, two holes motion is equal to one electron when coming to the conductivity point of view. Now, even though if you take the intrinsic material, 100% it is not electrons or 100% it is not holes. That means the charge is due to the 50% of holes and 50% of electrons. No, in the practical scenario, for example, if I want to design a switch, what is the perfect ideal switch case? If I am turning on the switch, 100% current has to flow. If I am turning off the switch, zero current. Now, if you are having only 50% of electron, now you cannot achieve 100%. That with the help of a 50% electron. Okay. Now that's why now what we are going for the doped semiconductor. Now what we are doing for the purest form of semiconductor intrinsic material, if you are adding some dopants to the intrinsic semiconductor material, now we are increasing the carrier concentration. Now the I am taking an example. Intrinsic material 50 holes, 50 electrons are there. Now if you are able to increase the number of electrons from 50 to 100, so that electron charge will be more compared to the hole. Now so that the 50% of efficiency I may increase it to 70 to 80%. Or now if I want to consider the hole charge, now if I am able to increase the hole charge, hole content concentration from the 50 to 100, now so that hole current is more compared to the electron current. Now this we can achieve with the help of the doping concept. Now that's why these extrinsic semiconductors are nothing but your doped semiconductor. Now to whom we are doping? To the intrinsic semiconductor. First base is intrinsic semiconductor. Adding the impurities to the intrinsic semiconductor, we are getting the extrinsic semiconductor. Now there are two types of extrinsic semiconductors are there. N-type semiconductor and the P-type semiconductor. What is an N-type semiconductor? If you are doping an intrinsic semiconductor with the pentavalent impurities. What are the pentavalent elements? The valency 5 elements: arsenic, antimony, phosphorus. That means this is an phosphorus atom I am taking. This +4 is nothing but your silicon or germanium crystals. Now if you add one dopant, that means one impurity atom, one pentavalent impurity to this silicon structure. Now what it is a valency 5 electron. These 4 electrons, they are bounding with the 4 surrounded by the 4 silicon crystals, and it is leaving the one empty electron. That means if you dope with one phosphorus atom, it is giving one excess electron. Now if I dope 100 phosphorus atom, 100 excess electrons I am getting. If you dope the 1000 excess electron, in this way you can increase the carrier concentration. That means electron concentration you are increasing in the form of doping with the pentavalent impurities. Now if you are doping with the pentavalent impurities, the type of conductor is N-type semiconductor. In case of N-type semiconductor, now what are the majority charge carriers? Every atom is giving us one excess electron. That's why in the N-type semiconductor, electrons are the majority charge carriers, holes are the minority charge carriers. That's why the number of free electrons is very, very high compared to the number of holes. Because here we are not increasing the holes. In the intrinsic semiconductor, how many holes are there? That many holes will present. But the electron concentration you are increasing by doping with the pentavalent impurities. This you are calling as N-type semiconductor. Now same vice versa, the P-type semiconductor. What is the P-type semiconductor? Now if you are doping with the trivalent impurities, what is the valency 3? That is indium, boron, indium, gallium, aluminum. These you are calling as your trivalent impurities. Now if you are doping with the trivalent impurity, I am taking a best example. This is not germanium. There is a printing mistake is there. It is a boron atom or boron or aluminum. This is surrounded by the germanium or silicon atoms. Okay, now it has valency 3 only. These 3 electrons, they are forming 3 electron hole pair concentration. They are forming the 3 covalent bonds with the 3 surrounded atom. And with the 4th atom, it is creating a space that you are calling as a hole. That means every trivalent impurity that is creating one hole. Previously, in the intrinsic concentration, for example, 50 holes are there. Now with this excess one, 51 holes will be there. In this way, you can increase the positive charge carrier concentration. Now, in case of this P-type semiconductor, now if you are doping with the trivalent impurities, what are the majority charge carriers? Holes are the majority charge carriers and the electrons are the minority charge carriers. That's why in case of P-type semiconductor, number of holes will be very, very high compared to the number of electrons. This is related to your p-type semiconductor. In the last class, just I already explained you this band diagram also, but people are not able to see the slide. Now, what is a donor ionization and acceptor ionization? Who is the donor? The pentavalent atom is donating the electron. Okay, who is acceptor? The trivalent impurity. It is because one hole is there. Now it can accept one electron. Now everything. Now next class, now to present today class onwards, we are going to see the band diagrams, because you will get the full picture with the help of this band diagrams, the full concept, clear concept, so that you can easily write in the examination. Okay, the excess electrons in the donor atoms. That means if you are doping with the pentavalent atoms, they are forming the excess electrons. They are forming as one energy level. That is ED. That is just below the conduction band. Now see, all the donor atoms. That means you are added with the pentavalent impurities to the intrinsic semiconductor. The excess electrons are there. These excess electrons, that is I am calling as a donor electron, donor atoms. They are forming as an energy level that you are calling as a donor energy level. Where is this donor energy level? It is exactly near to the conduction band. Remember this. Now these are the excess electrons. They are near to conduction band. Now what will happen? Now with a small energy, even at the room temperature, these electrons, they can easily move to the conduction band. Now this is the ionization process. Before ionization, now this is the thing. All the excess electrons they are forming as a donor energy level. After ionization, now you are not supplying some external energy. Only at the room temperature, they can easily move on to your conduction band. This is for donor ionization. Now same thing for the acceptor ionization. Now in case of acceptor ionization, where are the holes? These holes are near to the valency band. Now see, these are the holes. These are not electrons. All these holes, they are forming as acceptor energy level. At the room temperature, these electrons in the valency band, they can move to this acceptor energy level. Now these electrons, they move to this level. They are creating the holes here. Is it clear? Now this is nothing but in these two slides, the previous slide and this slide, just what I am going to conclude is, in case of donor ionization, the donor energy level will be at the near to the conduction band. Acceptor energy level, which is near to the valency band. Just only remember these two things. And this is a summary in the last class, just what I discussed. And in the intrinsic carrier concentration of the purest form of material, N is equal to P is equal to Ni, it has equal number of electrons and holes. Addition of acceptors, in the sense, if you are adding the acceptor means, if you are adding the hole means, they are doping with the trivalent impurities, that is creating the p-type material. In this, number of holes are high compared to your number of electrons. Very high, not a normal high. It is greater than, double greater than. Addition of donors. Donor in the sense excess electron. When the excess electron will come, that means doping with the pentavalent atom. If you are doping with the pentavalent atoms, that creating the n-type material. In the n-type material, the number of electrons are very high compared to the number of holes. Okay, this is what we discussed till now. And for all the materials in the equilibrium, what is the mass action law? Np is equal to Ni square. Okay, this is what I discussed in the last class. Now this is a basic summary of what is basic solids you're having. What are the semiconductors? What are the differences between intrinsic semiconductor, extrinsic semiconductor? And about the charges we discussed. What are the majority charge carriers in n-type material? And what are the majority charge carriers in the p-type material? Now with this concept, now we can move on to our today's topic. The today's topic is nothing but the p-n junction diode. Now we will combine the p-type material, n-type material, and we will see now how the operation will be, now how the bands they are going to move, and everything we will discuss. Is it clear? The first introduction slide. Shall I move on to the today's topic? Just can anyone the ping me, any CRs or anyone? Shall I move on to the today's topic? Am I audible? Okay. Okay, now we'll start our today's topic. The today's topic is the PN junction diode. Okay, now I will go a little bit slowly because if you get the full clarity about this PN junction diode, then the remaining concepts, it is going to be very, very clear. Okay, 1 minute. Once again, I will come back. Okay, here also we are having some 4 to 5 slides. Is it visible? My slides are visible to you, everyone? Okay. And now there is just first 4 to 5 slides are what I discussed till now. I will go very fastly. Now, what is an intrinsic semiconductor? It is the purest form of semiconductor. A crystal of pure and regular lattice structure is called as intrinsic semiconductor. What are the materials, intrinsic materials we are having? Silicon, germanium, or the gallium arsenide. Silicon is today's IC technology is completely based on the silicon material because silicon is very abundant in nature. Silicon is nothing but the sand, silica, what we are calling. And the germanium is early we are going to use the germanium, but compared to the silicon, the germanium is the cost of production is a little bit high compared to the silicon. Now that's why mostly we are preferring the silicon based materials. This gallium arsenide we are going to use in microwave circuits. That is not related to you. You see people, they can know very well. And now see, there is a small definitions we are having. 3 definitions are there. Now I will give you the full clarity. Now what are the carriers? Now what is a drift current? What is a diffusion current? So these 3 things are clear. Now it is going to be very clear. Now what are the carriers? Carriers are nothing but a free electron is a negative charge and a hole is a positive charge. Whenever I am calling electron is nothing but it is having a negative charge particle, negative charge carrier, hole is a positive charge carrier. Both of them can move in the crystal structure. They can conduct electric current. Once again, I will read the same statement. Electron is a negative charge carrier. Hole is a positive charge carrier. Both can move in the crystal and they can conduct the current. Now, how the current direction? The electron is moving from the left to right. Current direction will be in opposite direction. Already you know these basics. Once again, I'm recollecting. The hole is moving from left to right. The current direction will follow the hole moment. Once again, I'm giving. If the electron is moving, the current direction will be opposite to that of movement of electron. If the hole is moving, the current direction will follows the hole moment. Now, this is a small thing related to your carriers. Now, what is the doped semiconductor? Just now we discussed the doped semiconductors are the materials in which carriers of one kind is predominant. Only 2 types of doped conductors are there. The conductivity of doped semiconductors is much higher than your intrinsic semiconductors. The PN junction is formed by doped semiconductors. Okay, now see these 2 slides. Focus on these 2 slides because I am coming to the terminology point of view. If this terminology is clear, then PN junction diode, it is going to be very, very clear. Now, what is the terminology of N-type semiconductor? The basic concept is doped silicon in which the majority of the charge carriers are the negatively charged electrons is called the N-type semiconductor. It is clear. That means in which the electrons are the majority charge carriers, that is the n-type semiconductor. Now in this, the three types are the terminology is there. What is the terminology? Here excess electron is there, that's why it is calling as a donor. Now what is a donor? It is n-type semiconductor is having the donor because impurity is providing the free electron, usually entirely ionized it is. Okay. Now what is positively bound charge? It is impurity atom that donating the electron gives rise to the positively bound charge. In the next slides, I am going to show you this p-type, n-type combining p and n-type. Donor. Why in the n-type semiconductor, the terminology we are calling it is a donor? Because excess electron is there, it is providing excess electron with the help of impurities. That's why you are calling it is a donor. Donor, and it is positive only. If you are having more, then you can donate. That's why the charge, the bounding charge is a positive bound. Ions are nothing but the positive ions are having. What are the carriers? The free electrons are the majority charge carriers, holes are the minority charge carriers. Now this slide you will get picture with the help of your diagram. I will show you the diagram. Now what is the p-type semiconductor? The concept is in which holes are the majority charge carriers. Terminology is it is acceptor because it is creating a hole. That's why you are calling as acceptor. Accepting, that means it is negative in nature. That's why you are calling as a negatively bound charge is there. The carriers or holes are majority charge carriers. So electrons are the minority charge carriers. Now two more things we are having. What is a drift current and diffusion current? These two types of currents we are going to see in the complete analog electronics part. Not only in PN junction, in the BJT, field effect transistor, everywhere we are going to see this drift current and diffusion currents. Now what is the difference between these two? What is a current basically? It is generated by the movement of charged particle. If any charge, what is charge particle? Electron or hole. If electron is moving from one place to another place, it will constitute a current. Or a hole is moving from one place to another place, it will constitute hole current. Now that means movement of any charged particle that will constitute a current. That may be negative charge or a positive charge. That may be. Already I told you carriers. The charged electrons and holes are the carriers. There are two types of currents are there. First one, drift current. Drift is if any charged particle is moving with the help of external electric field. That means if you are applying any electric field with the help of electric field, if any charged particle is moving, means that is a drifting current. Drift current. Drift current is if you are pushing an electron with the help of external supply. Now electron is moving from one place to another place, that is causing a current. That current is a drift current. Is it clear? The drift current is, it is a current caused by the electric field. That means externally you are going to supply some energy. Then only electron can move from one place to another place. If it is moving means it is causing the current. That current is a drift current. What is the diffusion current? In the diffusion current, you are not supplying any energy due to the concentration ingredients. That means, for example, if one side 100 electrons are there, another side 10 electrons are there, due to the concentration mismatch, these 100 electrons, they can easily move to the 10 electron side and they will become the balance, the 50-50. It is becoming the concentration is becoming 50-50. Now that type of concentration ingredient you are calling as a diffusion current. What is a diffusion current? The diffusion current is a flow caused by variation in the concentration. That means one side higher number of electrons are there, another side lower number of electrons are there. Due to this concentration mismatch, the electrons will move from one place to another place. Whenever electron is moving, it is causing the current. That current you are calling as a diffusion current. I hope these two terms are clear. Once again, I am giving the picture. Drift current is nothing but applying external electric field. With the help of electric field, it is moving means that is a drift current. Without applying any electric field, automatically electrons are moving from one region to another region, that you are calling as a diffusion current. Right. Now what is a drift current? Now see, if you take a n-type material, and now if you apply any external electric field, due to this electric field, if the electron is moving, then this you are calling as your This is the current is electron is moving in this direction. Current is opposite direction, electron movement direction. This you are calling as a drift current. Main thing is drift current is nothing but in presence of electric field, presence of external supply, external energy. What is a diffusion current? Flow of particles. The particles may be electrons or holes from the region of high concentration to the low concentration. Generally, the movement of the particle will then cause the diffusion current. I hope this drift current and diffusion current will be clear to you people. Is it clear? Drift current, diffusion current, and the carriers. Shall I move on to the PN junction? Okay, right. Now, what is a PN junction? And now this is the PN junction diode, the symbol we are having. It is if you combine P-type material, N-type material, that is forming a junction that you are calling as a PN junction, that you are calling as a diode. Diode is having the two terminals. Triode is having the two terminals. That's why it is calling as a diode. It has a two terminals. First one is the anode, second one is the cathode. I think already if people know about this PN junction diode symbol, all those things, these concepts. Now once again I'm showing the P-type material, N-type material. The symbol of PN junction diode is it is a triangle with a vertical line. Now this side is the anode. This you are calling as a cathode. This is a practical diode you are having. Now whenever the lab classes will start, now you people are going to, you are having the laboratories there. Now there you are going to deal with this type of diodes. N4004 diode is a practical diode symbol it is. Now, now the two slides, the previously already I discussed about the terminology of N-type and P-type. What is an N-type? It is a donor. It has a donor. This is a donor ion. That's why it is positively surrounded. Positively surrounded the excess electron. This is your donor. This is a donor ion with an electron, excess electron. What is an P-type material? Acceptor ion is negative. It is negative surrounded by, it is majority charge carriers are your holes. Now that two slides, the picture is, this is the picture. In case of N-type material, electrons are the majority charge carriers. At the same time, they are having the positive ions. Now in case of P-type material, holes are the majority charge carriers. They are having the negative ions. And this is the picture of those two slides. Right. If I am combining the P-type and N-type material, now here I am not taking the ions into consideration, because in the P-type material, it is a negative ion surrounded by the holes. Just I am considering the majority charge carriers. In the P-type material, the left side is the P-type material, right side is N-type material. Okay. Now the P-type material majority charge carriers are your holes, minority carriers are your electrons. N-type material majority charge carriers are your electrons, minority charge carriers are nothing but your holes. Okay, if you are combining the P-type and N-type material, already they are having, within this region, this side electrons are there, this side holes are there. This electron hole pair recombination will take place. Whenever, because you are not applying any external supply, just it is without any supply, with no supply. Just I combined P-type material with N-type material. Immediately, this is line your, this is a N-type and this is a P-type. The electrons near to this junction, holes near to this junction, they will form as a electron hole pair recombination. Whenever electron hole pair recombination takes place, they are going to be disappear, and they are leaving the immobile ions. These ions, they are not going to move. See, ions are the fixed one. Who are going to be movable? The electron charge carriers will move. That means these holes and electrons, they can move in the N-type, and these electrons and holes in the P-type, they can move, and these ions will be, they are fixed ions. Now, whenever you are combining the P-type material, N-type material, there is a region, the depletion region, space charge region is going to be formed. That means these electron and these hole pair recombination will take place, and they are leaving the immobile ions. That means there is a negative ions at the P side and the positive ions at the N side. Let's see the simple terminology, what is going to happen here. And now, when you join the two materials, the electrons and the holes in the region of the junction, okay, now region of the junction will combine, resulting in a lack of free carriers in the region. Here there is no charge carriers. In this region, there is no charge carriers. Now, beside this, there is positive charge and negative electrons are there. So beside this, holes are there. Charge carriers will present in this side and this side, but in this region there is no charge carrier. Note the only particles displayed in this region are the positive and the negative ions remaining after the absorption of free electrons. The region of uncovered positive and negative ions, this region we are calling as the depletion region. The other name of depletion region is phase charge region. Like I hope this is clear because already you studied in the physics part also. Just nothing I did. I combined the p-type material, n-type material. When you are combining the holes, the p-type holes are majority charge carriers, and this n-type electrons are majority charge carriers. Now, these two will be very near. That's why the one electron, one hole recombination will take place. Now, for example, if this electron is having energy to recombine with these holes, now this also they can recombine. But initially you are not applying any voltage here, any electric field here. Now that's why side by side, this electron, this hole recombination takes place. They are leaving some immobile ions. This region you are calling as a depletion. Depletion. That is, charge carriers are depleted. There is no charge carriers in that region. This is the meaning of your depletion region. This is a simple value if I am combining the p-type and n-type. Now this is a simple space charge region you are having. These are ions. These are not charge carriers. These are not surrounded by the circle. These are the negative ions. These are positive ions. Generally, this is not the size of the depletion region initially. Very small. Only one electron, one hole recombination will take place. Now here, the main importance of this slide is I want to show you the different currents in this PN junction. Now, what are the different currents? Two types of drift current is there, diffusion current is there. What is a diffusion current? Diffusion current is movement of electrons or holes from higher concentration to lower concentration. In case of P material, holes are majority charge carriers. N-type holes are minority charge carriers. Now, if any hole is moving from P to N, because take an example, here 1000 holes are there, here 100 holes are there. Due to the concentration gradient, these 1000 holes, if they are moving to the N-type, in the p-type material, holes are majority charge carriers. When they are coming to the n-type, the holes are minority charge carrier. Now, that's why see the hole current. The holes will diffuse in which direction? The holes will diffuse in this direction. See the arrow mark. That means majority holes are there. They can diffusing to the minority side. Because whenever hole is moving in this direction, electron current direction is also in the same way. Okay. Now, coming to the electron diffusion. Now, N side electrons are majority charge carriers, P side electrons are minority charge carriers. Due to the concentration difference, these electrons they are moving to the P type. Now, electron is moving from N to P side. What is the current direction? Opposite direction. Now, that's why what is the diffusion of electron? Electron diffusion will be in this direction. Okay. Next one is drift currents. Now, drift currents we are going to discuss in the next one we are having. This is a simple thing. Diffusion current in this way and diffusion current in this way. The hole is moving in this direction, then the whole current is going to be follows. The electron is moving from N to P, current direction will be opposite. Okay, sorry, this is in different direction you are having. The whole direction is this way it is coming. If the electrons are moving from this way to this way, current direction also will be in this way, in the same direction we have. See, this is in quite opposite direction. Stick to the concept. What is the concept? The electron is moving from N to P. Electron is moving from N side to P side. Current direction will be opposite direction. What is the direction? This is going to be this way. It is arrow mark we are having. See here. And now this is this way it is having. Sorry, here it is a mistake is here. Because electron is moving from this way to this way. This electron is going from higher concentration to lower concentration. Current direction current, not electron diffusion. This is electron diffusion. Just correct the slide. Okay, this is clear. Now, what is the diffusion? As free electrons and holes diffuse across the junction, a region of fixed ions is left behind. This region is called as the depletion region. Now, so initial Ft is equal to 3 electrons. This electron and hole recombination takes place. They are leaving the positive ions and negative depletion. T is equal to infinity. Just these last 5 minutes, I am discussing about the same concept. So only when you are combining p-type and n-type materials, the depletion region is going to be formed. Depletion knows charge carriers. Okay, that is the concept. Yeah. Now this is an important thing. Open band structure. This band structure is very, very important structure for us. If it type next to 10 minutes of class. Now I told about the valency band, conduction band, and where else will be there, where the band. If you take the p material, see this is the dotted line, left side part is the p type. This part is nothing but your n type region, n material. In the p region, n type material, what are the majority charge carriers? Where are the holes? Holes will be there in the valency band. The valency band is completely filled. Now that's why majority holes are there. Valence very, is it clear? Now the Fermi level is near to the valency band here. Remember this. Now coming to the n majority charge carriers. Now that's why where the electrons they are in the donor energy level will be there. Now at the room temperature, majority electrons they are in the conduction band. Is it clear? In the p-type material, electrons will be there in the valency band. Majority charge carriers are holes, but they are going to be there in valency band. In the n-type material, majority charge carriers are electrons, they are in the conduction band. Now there is a difference. Now see, you are taking this is a wall. Now, for example, this is a conduction band electrons are there. If this n region electron, for example, here electrons are there. This is a conduction band of n-type material. This conduction band of p-type material. For example, here one electron is there. If electron is want to move to the p-type material, is it possible? Is the electron can move freely from the n-type to p-type material? No. I will take a pointer here. Right. Now, here one electron is there. If this electron I want to move from n-type to p-type, it is very, very difficult because the height of this band is very, very high. Now, reducing the height of the barrier, for example, if this height is at this height only, this height is now in the open circuit junction. Now these electrons in the conduction band, they cannot move it. That is how the discharge region, one electron, one hole will be they are recombined. The remaining electrons in the n side, they are not able to be. There is a build. There is a this barrier is there. This barrier is obstructing to move to n. Now, will move freely from n to p or p to n. If this barrier height, if you are reducing this barrier height, then the freely they can be clear. This is I am not applying any supply. Now, in the majority charge carriers, holes they will completely occupy the valency band. That's why valency band is very larger compared to the n-type region. Electrons are majority charge carriers. Now this Fermi level is, this is the Fermi level is the middle of the level. It is near to your simple of your diode. Open circuit is I am not connected any supply to this simple thing. Right, this is a small, just now I explained the open circuit value Vi is equal to 0 if I am not applying any bias. Now what is going to happen if you are not applying any bias? See that this is a barrier height. These electrons because the barrier height is very, very high. Now any electron or hole that wanders into the depletion region, that's why if no applied voltage, drift current is equal to diffusion current. That means if you are biasing voltage, now initial recombination will take place. They are forming as a depletion region. In the depletion region, there is no charge carriers. Now you may get one doubt, sir. In the if you are now where is the diffusion current? Where is the drift current? You may get one doubt. Now see here. Now take this as a value. Now what is an current? Current is movement of electron is nothing but a current, or movement of hole is nothing but a current. In the open circuit connection, that means you are not applying any electric supply at the outside. Now when you are combining P type and N type, there is a different amount of that you are calling potential. Now here hole is there, now here electron is there. Directly they cannot recombine. This electron moving this coming nearer to this, they are combined. That means electron was moved to some distance. Hole was moved to some distance. Due to the movement of electron hole, going to be diffusion current. Now see as a diffusion current. This is not drifting current. Okay. Now what is, where is the drift current? Drift current is nothing but, now see, this is the barrier. Remember, depletion region. Due to this depletion region, majority charge carriers they are not able to move into this side. But minority charge carriers they can move. What is the here minority charge carriers, sir? Electron this I'm calling out minority charge. Electron comes to this side. It is becoming majority charge carrier. Whenever hole is charge carrier. Due to the movement of there is all minority carriers, the current constituted is called as your drift current. Now you may get wonder what happened. Now there is an electric field. Where is that electric field? This positive ion. This is a positive ion. Now these particles are minority carriers. See, due to the depletion region, major they can positive electric field is there. Ion is nothing but it is having some electric field. Is a negative electric field is there. This positive is attract carriers, negative attracting your matters. Now electric field. See, this is not a large number of holes and electrons will not move. Only minor drift current. In case is mobile ion, charge carriers due to electric field only they are attracting. The electric field is there. That's why that current you are calling as a drift current. But ideally, there is small amount fraction of very microamperes of current. when no applied bias condition, there is small. The drift current and diffusion current will be the small. Now, when the current will majority charge carriers are moving, that is a maximum current. Just keep it in your mind. If the majority charge carriers, amount of current will come. The minority charge carriers they are moving means there is negligible amount of current. You are not going to consider that amount. Reverse saturation current, that you are not going to consider that amount also. That is calling as a drift current. I hope this is clear. Now see, electron can move if it is in the same height. Then cannot directly go to this way. This is the simple one. Right. This is with no bias condition. The first one is just I combined the p type and n type material. This is just I combined p and n type material, and just I observed what is a diffusion current, drift current, what is an depletion region. That is what I discussed till now. The band structure also I discussed. Now what about the status of conduction band? What is the status of valency band? Where is the Fermi level? That is I discussed till now. Now I am doing the biasing concept by applying the bias. Now there are two types of biases there. One is a forward bias. Second one is nothing but your reverse bias. I think today we are having only 5 minutes. We will start the full. Now I will discuss the biasing of PN junction in the next class. I will continue the same thing. Now shall I start the test? Just anyone, can you give me the reply in the chat box so that I can run the test? Okay. Okay, okay. Okay, I think all of you already logged. If I justify, I'll stop the